All right. Same, just another question 3 about closed form. Okay, and then A12 question 2. All right, hold on. I got to write some stuff down. So same question 3. And then 329B and then A12Q2. Okay, so using scheme RST, you'd like to set up a 3-year annuity where you're able to withdraw $8 from the account. Okay, what's scheme RST again? Scheme RST, R at the end of the first week, S second week, T third week. Okay, and then you repeat. Using scheme RST, you'd like to set up a 3-year annuity where you're able to withdraw $8 from the account at the end of each 3-week period. How much should your initial deposit be? Right, okay. And then so specifically, I assume it's sort of the whole thing. Devin, you're kind of saying the closed form thing. Complete your initial deposit if you'd like your annuity to be $8 instead. Okay, sure. So, wait, where does the 50? Oh yeah, because it's each week. All right, so we're assuming a 52-week year. I guess I should write this is term test 3, question 1, right? Yeah, this would be posted on YouTube. I am recording. Okay, so RST, right? We've got R at the, oh yeah. Thank you. So we've got R at the end of the first week. We've got S in the second week. And we've got T in the third week, right? Okay, so in 1 year, what do we have? 14 of each, right? So in 1 year, there are 14 of each compounding period. Or let's say compounding, or like rate. There's 14 of each rate, right? So, you know, if here's the end of year 1, here's the end of year 2, and here's the end of year 3. So we have $8. Did I say at the end of each year? And 3, we're able to, from the end of each, from an account at the end of each 3-week period. Oh, at the end of each 3-week period. Oh, okay. So at the end of each 3-week period, I guess how are we going to do this? Here, maybe let me draw this out. So maybe here's year 1. And then we've got 3 weeks, 6 weeks, 9 weeks, 12 weeks, ... all the way up to 52 weeks, right? Now, in each of these 1-week periods, you have an R and an S and a T, right? So you have an A here, an A here, an A here, an A here, ... and an A here. So when I bring these when I bring each of these payments back to time, back to the present, right? I get an A, 1 plus R to the -1, 1 plus S to the -1, 1 plus T to the -1, right? When I pull this one back, I see each period twice. So this is A, 1 plus R to the -2, 1 plus S to the -2, 1 plus T to the -2, and so on and so forth, right? So this one would come back and I would see 3 of each period. 1 plus S to the -3. And so after 1 year, this is what, 14 time periods? So A, 1 plus R to the -14, 1 plus S to the -14, 1 plus T to the -15, or 14, sorry. Right? So now the question asks for 3 years, but again, if you can't kind of figure it out for 3 years, you know, start with 1 year. So after 1 year, so the 1 year present value is going to be the sum from K equals 1 to 14 of A, 1 plus R to the -K, 1 plus S to the -K, 1 plus T to the -K, right? Now the question says, you know, you do it for 3 years. So the only difference is, you know, that you've got to do it for 3 more. And so there's 14 and the 14 of these things in the first year. Therefore, there's 28 after 2 years. And like, what is that? No, wait, 14 times 3. Why do I feel like I screwed that up? That's only 42. Did I screw up the number of?
I think it should be 17, 17, and 18.
17, 17, and 18. Yeah, okay, wait, hold on. 52 divided by 3 is what? So, oh yeah, you're right. It is 17 1/3, right?
Yep.
Damn it. So that's why we did the 3-year period, because if you do it for a 3-year period, then there should just be 52 of each, right? Because you would do 52 times 3 divided by 3, and that would just give you 52 periods. Right, okay, so I guess it just makes more sense to do the 3-year annuity. So that would just be k equals 1 to 52. That's what I get for trying to break this into smaller steps. 1 plus t to the negative k. Right, so that's why we did it 3-year period. So does the question ask for a closed form, or does it say just to do this? Well, it wants the initial deposit, but I mean, technically speaking, I think I didn't say to give a closed form, but if we wanted to do a closed form, we could then plug this into our formula, right? So what's our formula? So we have the sum from k equals 1 to n. Somebody remind me what this formula is. So r to the k is what? R times 1 minus r to the n divided by 1 minus r, I think, right? Maybe I should use a different r so that we don't confuse it with the r that we have above. So here my r is 1 plus r to the negative 1, 1 plus s to the negative 1, 1 plus t to the negative 1. So I would get a times this thing. I don't want to write it out. 1 plus s to the negative 1, 1 plus t to the negative 1 times 1 minus that thing again. 1 plus s to the negative 1, 1 plus t to the negative 1 divided by, oh, sorry, that should be n. 1 minus 1 plus r to the negative 1, 1 plus s to the negative 1, 1 plus t to the negative 1, like that, right? And then it says you're going to convert that into a perpetuity. Great. So for a perpetuity, you would just make it k equals 1 to infinity, right? A 1 plus r to the negative 1, or negative k, 1 plus s to the negative k, 1 plus t to the negative k. And what's our formula? So k equals 1 to infinity of r to the k is r over 1 minus r. So in this case, we would get a 1 minus 1 plus r to the negative 1, 1 plus s to the negative 1. Or sorry, not 1 minus. 1 plus t to the negative 1 divided by 1 minus that. Like that, right? And is that what I got? Yeah, that looks right. So does that make sense? Like whoever asked for this one, can you pinpoint like maybe a specific area of this one that was bugging you, or? Was it the 52 times 3? Because that kind of burned me, but because I thought in my head 52 divided by 3 was 14, and obviously it's not. Right, yeah, after week 3, exactly. Yeah, if it happened before week 3, you just kind of have to push everything down by 1, right? Okay, so 329 for not expanding the summation and getting a close form. Yeah, I mean, actually, I think at that time, it probably actually was that we were saying you always have to do closed form. So we were probably saying that. I don't remember exactly from the time, but I suspect we were probably saying, yeah, you got to do a closed form. So 329b. Oops, what did I just do? Okay, so 329b. And so it says find the determinant of what? 1, -1, 2, 1 plus a, -1 plus a, Oh yeah, okay, never mind. This isn't too bad. There's a hack to this. 2b, negative 2b, and 4b. Okay, great. This is 0. And the reason is that I can look at this and I can say this matrix isn't invertible, right? Notice that the third row is 2b times the first row, right? So the third row is equal to 2b times the first row. Everyone agree? And so since that's true, and in fact, what else do we know? I think we also know, do we have something else? I think the second row might also, maybe it's not, the second row isn't, oh yeah, because we subtract a. Anyway, it doesn't matter. Third row is 2b times the first row. That means that this matrix does not have full rank, right? Basically, if I were to row reduce this, and I were to say, take row 3 minus 2b times row 1, I would get this, I'd get this row of zeros. And because I get this row of zeros means I don't have full rank. Because I don't have full rank, I'm not invertible. Because I'm not invertible, my determinant is 0. Does that make sense? You could work it out. You could actually compute it. And I'm happy to do it if anyone wants an example of us actually to like write out a determinant calculation. But the thing that I really want you to do from this is to be like, to look at this and be like, this is not an invertible matrix. So its determinant is immediately 0.
Initially, I was going to say that column 1 and column 2 were just the negation of one another, but then I realized the -1, it's -1 plus a, not -1 minus a.
Yeah, which kind of throws that up a bit.
Yeah.
So does that make sense? Does everyone see why the determinant of this is 0? Does anyone want us to do this as like a long, complicated algebra exercise? Yeah, okay, so let's say, like here, maybe let me sort of write out this. So note that if we were actually row reduced this, here, let me just maybe copy this so I don't have to do it, write it all again. Okay, so what I could do is negative 2b r1 plus r3 into r3, right? If I did that, I would get 1 plus a, negative 1 plus a, 2 minus a, 0, 0, 0, right? And so that tells me that this matrix does not have full rank, right? So it has rank less than or equal to 2, right? And for a matrix to be invertible, so it needs to be square, first of all, and this is, but you need to have the same rank as you do, number of columns, right? You have to be full rank. Right? When you row reduce, when you put your matrix into reduced row echelon form, you have to get the identity matrix out. That's critical, right? That's the condition for being invertible, is that if we do that row reduction, we actually get the identity out. So there's no way I'm going to be able to get the identity matrix if I row reduce this, which means that it's not invertible. And remember, we know that a matrix is invertible if and only if its determinant is not 0. So because this matrix is not invertible, its determinant must be 0. Does that make sense? Again, you could actually do it, right? You could go through the motions and actually compute this thing, and you would actually get 0. It's just, it'd be a little bit long to do, right? And again, it's a little bit tricky because there's some algebra. So is that okay? Does anyone want us to do the actual determinant calculation? Sure. With the caveat that you're all going to have to double check my math. Okay. What row or column should we expand along? What do you guys want to do? Row 1, column 1, row 2, column 2. Any preferences? Someone pick something.
Row 1.
Column 1.
Okay. Well, Brandon was the first student who answered, so we'll say row 1. Okay, so along row 1. Okay, so we're going to get 1 times the determinant of that submatrix. So let me just write that as a minus 1 instead of negative 1 minus a. And then 2 minus a, which I actually kind of want to write as negative a minus 2. I just prefer to have my variables first. Negative 2b 4b minus negative 1 times the determinant 1 plus a. Well, now here I'm doing it again. So a plus 1, negative a plus 2, 2b 4b, and then plus 2 times the determinant a plus 1, a minus 1, 2b, negative 2b. All right. So we're going to get 1 times a minus 1 times 4b minus negative 2b times negative a plus 2 plus a plus 1 times 4b minus 2b times negative a plus 2 plus 2 times a plus 1 times negative 2b minus 2b times a minus 1. And we'd have to expand all this out. So let's see. Do we get any really nice, obvious cancellations here? So we get a cancellation here, right? So that's going to give me a 4b plus a 4b. So that's going to be 2a 4b. So that's going to be 8ab. Then I'm going to get positive 2b and then times negative a. So that's going to be negative 2ab. That's going to be another. Oh, that's a positive 2ab. So these two things are actually going to cancel each other out. Then I'll get minus minus a plus. So that's going to be 4b. Here's plus 4b. So I think that's an 8b. And then here, what am I going to get? So I'm going to get minus 4ab minus 4b, then minus 2ab plus 2b. That's a little bit weird. Where did I do my algebra?
I think you're slightly off. The 8b, where do you get that second 8b?
All right, here, let's just expand it out. Let's do it by hand. Okay, so we're going to get 4ab minus 4b. Let me just make these pluses. So we're going to get minus 2ab plus 4b, right? So that's that first bracket, plus 4ab plus 4b. And then this is going to be plus 2ab plus or minus 4b, right?
Yep.
Plus, so negative 2ab minus 2b minus 2ab plus 2b.
There's a 2 in front of this whole bracket.
Yes. Oh, and that's actually, yeah, that's the thing I was missing before, was that extra 2. Okay, so let's see. So what's going to cancel? So first of all, we've got a 2b here and a positive 2b here. So these two things cancel each other out. We've got a negative 2ab here and a positive 2ab. Those cancel. We've got a negative 4b and a positive 4b. So those should cancel. We've got a 4b and a negative 4b. So those cancel. Okay, so.
And then everything else cancels off.
Yeah, so it should, right? So we get 8ab, and then here we're going to get minus 4ab, and then another minus 4ab, right? So that, yeah, that's equal to 0.
It would have been a lot easier if you realized the trick from the beginning.
Yeah, right. But like, whatever, it works out. So even if you don't see the trick, you can do it and everything will cancel and you'll get 0. So it's a little bit of work, but if in doubt, you can do that. A12 question 2 is the next one, which I think I've posted solutions for. I have, but maybe we just want to like see how it sort of work. Internet. All right. So A12 question 2 is, so we've got this function f(x, y, z) is what? X, y, e to the negative x squared plus y squared plus z squared. So we have to compute the question is, find the critical points basically of this thing. So we have to differentiate. So if I compute the x derivative, what do I get? So I'm going to have to use the product rule here. So I'm going to get y e to the negative x squared plus y squared plus z squared. So that's the derivative of the first times the second plus the derivative of the second. So that should actually give me a negative 2x squared y e to the negative x squared plus y squared plus z squared. Now this equation is completely symmetric in x and y. So when I differentiate it in y, I should get the same thing just with x and y reversed. Okay, and then when I differentiate it in z, it's nice because I just don't have to use, wait, did I? No, yeah. So I just don't have to use the product rule. So I should just get negative 2x, y, z e to the negative x squared plus y squared plus z squared, right? So far, so good. Right, so I get this thing. And if I, factor out some e exponentials, I'm going to get y times 1 minus 2x squared e to the stuff is equal to 0. X times 1 minus 2y squared e to the stuff is equal to 0. And then negative 2xyz e to the stuff is equal to 0. And the exponential is never 0, right? So you can basically get rid of it. And now you're left with this system of equations. And then I'm going to get rid of the negative 2 here because it's just sort of annoying. X, Y, Z is 0. Okay. Now, there's a bunch of places you could start, right? And again, we have to solve all three of these equations simultaneously. For me, actually, I kind of want to start in equation 3 because it's nice. It sort of gives you information about X and Y and Z, whereas equation 1 only can tell you something about X or Y, right? Same thing with equation 2. So I kind of want to start with equation 3. Here, maybe let's label these. This is 1, this is 2, this is 3. I look at equation 3 and I say, okay, well, one of these variables, at least one, it could be 2, could be all 3, but at least one of these variables has to be 0, right? So from equation 3, either x equals 0 or y equals 0 or z equals 0, right? And again, multiple could be 0, but at least one of these has to be 0. So now we can do cases. So if we do case 1, so let's say x is equal to 0 here. So equation 3 is satisfied. Equation 1 then becomes what? So if x is equal to 0, we just get y is equal to 0 here, right? And then there's no restriction on z. So this gives me, every possible z is an option. Do we have a limiting set? No. So the solutions for this are this thing, right? Case 2, y is equal to 0. That I'm pretty sure just gives us the previous answer. Gives us this. So same as above. So case 3 is where z is equal to 0. So now we still have equation 1 and equation 2. So if we look at equation 1, one of these two things has to be 0, right? So either y is 0 or 1 minus 2x squared is 0. So case 3a, let's say that y is equal to 0. Okay. Now, if y is equal to 0, equation 1 is done. So equation 2 becomes x is equal to 0. So that gives me the solution 0, 0, 0. But that solution is actually already here, so we didn't actually learn anything new, right? So case 3b is where 1 minus 2x squared is equal to 0, i.e. x is equal to plus or minus 1 over the square root of 2. Now, if this is true, then we can plug this back into equation 2, which then becomes what? So we get plus or minus 1 over root 2 times 1 minus 2y squared is equal to 0. This obviously, the plus or minus 1 over root 2 in front doesn't do anything, right? Because it's just a number. So you can multiply and divide both, or multiply both sides by plus or minus 1 over root 2. So this tells us 1 minus 2y squared is equal to 0. So that tells us that y is also equal to plus or minus 1 over root 2. So this gives us 4 solutions, plus or minus 1 over root 2, plus or minus 1 over root 2, and 0. And then you're like, okay, that's my analysis of equation 1. Now, what if we said equation 2 is 0? But if equation 2 is 0, it gives me these 2 cases again. So I just have these 4 solutions and then these infinitely many solutions, and that's everything. Right? So you just go through all the possible cases that you can, and you kind of exhaust everything. When I put a quarter instead of 1 over root 2, but yeah, sure. Yeah. Okay, great. So that's how we do that. 3-22 I was also asked for. 3-22. Oh, this is a nice one. I think this was an assignment question one year. 226, okay, sure. So 322 is to find the determinant of this matrix. So C01, 2C, C1, C squared 0. So, we have to, again, sort of like choose a column or a row along which to expand. I think probably let's do row 1 again. Column 1 is also probably column 3 is probably a nice choice as well, but whatever. So if I compute this determinant, I get C times the determinant of C1, C squared 0, plus, well, here, maybe let me write it in, 0 times the determinant. So we don't need to put this in, but, we'll do it for completeness. Plus 1 times the determinant of 2C, C squared. So this is going to be C times negative C squared, oops, minus a big old 0, plus 1 times 2C cubed minus C squared. So this gives me negative C cubed plus 2C cubed minus C squared. So what is that? So that's C cubed minus C squared, looks like. So maybe I did that correctly. And then it says, so that's part A. Part B says, what values of C make C invertible, right? Oh, no, and it says, oh, so sorry, part A is for which values of C is C invertible. So, so capital C is invertible if its determinant is not 0, right? So we need to look at the equation C cubed minus C squared is equal to 0, or C cubed 1 minus C is equal to 0. This is equal to 0 precisely when C is 0 or C is equal to 1. So these are our 2 bad values. For these values, our matrix is not invertible. For everything else, it is, right? So C invertible if C does not equal 0 or 1. And then it says to find the inverse. Well, that involves us row reducing. So C01 to C1, C squared 0. 1 0 0 0 1 0 0 0 1. So we could do negative 2C row 1 into row 2, and negative C row 1 into row 3. So what does that give us? That gives us C 0 0 1 0 C, and then I said negative 2C, so that's going to be 1 minus 2C. It's going to be 0.
Shouldn't you have no C in your row operation?
Do I have no C in my row op? Where?
Shouldn't you have no C? Because if you're multiplying row 1 by 2C, you're going to get a,
you're right.
C squared factor.
Thank you. Yeah, thank you. You are right. You are right. Okay. So yeah, if I do negative 2 into that, negative 2, so negative 2, so this just gives me negative 1. Negative that. So I think this is just negative 1, right? So I got 1 0 0. Negative 2, so that would become negative 2 1 0, and then negative row 1, so negative 1 0 1. All right. And now I need to do negative C. Now there's 1 into row 3. So that gives me C 0, 1, 0, C, negative 1, 0, 0. So negative C just gives me C. So I'm going to get a C minus 1 here. 1, 0, 0, negative 2, 1, 0. And then negative C row 2. So that's going to be negative. So it's this 2C. So I'm going to 2C minus 1. Negative C and 1. Right? Okay, we can see the C equal 1 condition showing up here, right? If C is equal to 1, we get that like row of zeros there, which is going to be the issue. Yeah, okay, this is starting to get a little bit gross, but whatever. So let's just do 1 over C minus 1. Let's scale that row. Negative 1, 0, 0, 1. 1, 0, 0, negative 2, 1, 0. So I get 2C minus 1 divided by C minus 1. Negative C over C minus 1. 1 over C minus 1. Right? And then I'm just about done. Really, just 2 more steps. So we're going to do row 3 plus row 2, and then negative row 3 plus row 1. So that will give me the identity. This row doesn't change. Negative C over C minus 1, 1 over C minus 1. Okay, so I'm going to get, so let's see, row 3 plus row 2. So it's going to be negative 2 plus 2C minus 1 over C minus 1, 1 minus C over C minus 1, and then negative, so 1 over 1 minus C. No, wait. No, it's a straight addition. What am I doing? So 1 over C minus 1. And then negative that plus that. So this is going to be negative 1 minus 2C minus 1 over C minus 1, C over C minus 1, and 1 over 1 minus C. And then a lot of these simplify, like these simplify further. So you can work them out if you want. I'm not too worried about it right now, but you can do some algebra and figure out what they are, right? Like this simplifies really nicely, for example, right? Like that's going to be negative 1 over C minus 1. So yeah, you can do that. And that takes care of that. And then 326b. So 326, you just kind of have to, for you all right now, you just kind of have to guess and check. So right now it's saying find a matrix such that this is true. Y plus Z, X plus Z, X plus Y. And I can just see that an answer for this is going to be the following. So Y plus Z, X plus Z, X plus Y. So this should be 0, 1, 1, 1, 0, 1, 1, 1, 0. Right, just by inspection. Like I know that this has to be Y plus Z. How is that going to happen? Well, you know, we probably shouldn't have any X's, and then we should have 1 Y, and then we should have 1 Z, right? So that's why that row is that. So just sort of like guessing and checking or knowing how matrix multiplication works. Like don't try and solve this as a system. I think it's going to be too complicated. But if you just sort of like know how matrix multiplication works, you can see how this one goes. Okay, and then 226. Where's the? It's January 1st. You're given the option of receiving $1,000 today or $510 at the end of June and $520 at the end of December. Market rate 4% APR compounding monthly, which is better. Okay, someone's going to have to do the calculator checks for me. So 226. It's currently January 1st, so you can get $1,000 today on Jan 1, or, right, so that's option 1, or you can get 510 at the end of June. And you can get 520 at what, the end of December? Yeah.
Just a quick thing, Tyler. Jordan and I are probably gonna hop out. Just
okay. Sure.
Bye.
Yeah. See ya. So okay. So assume market rate 4% compounding monthly. Again, it's sort of like not clear whether we're compounding at the beginning or the end of the month. But let's assume it really shouldn't matter as long as we assume that you get the money at the end of that compounding period. So basically this, what we want to do is compute the present value, right? So I'm going to compute this thing. So it's going to be 510, 1 plus 0.04 divided by 12 to the negative 6. And then if I compute this thing, that's going to be 520, 1 plus 0.04 to the negative 12. And see if that's bigger than 1,000 or less than 1,000, right? So this is the present value of these two payments. And if this number is bigger than 1,000, you want this option because it's got the bigger present value. And if it's smaller, you just take $1,000 today. Right? So yeah, you'll have to work out what those numbers are because I don't have them off the top of my head. Does that make sense? Any questions with that? Right. So, which is pretty darn close, but is, so I'm being told that you can compute this and you get this. This is a worse number, right? So this is lower than 1,000. So you probably want the option, which gives you the more money, right? Like $1,000 today is worth $1,000. These two payments are only worth $999.56. You probably want the $1,000 today. No problem, Kelly. See you later. Okay, anyone else? Anything else? Hopefully that took care of some stuff. No problem, Devin. See you later. Okay, anyone else? Everyone's just waiting for someone else to ask something, right? Okay. Yeah, great. If something comes up, we'll be back here Thursday, right? So can ask then. Otherwise, if everyone's good, I think we can call it. Keep an eye out for that announcement, right? And then again, tell your friends, like, don't worry about it. Yeah, for sure. Cats is a great place to do that as well. Okay, so I'm not seeing anything incoming. In that case, I'll call it, we can call it a day. All right, thanks everyone. Thanks for coming. Yeah, for sure. Thank you, Ariana. Thank you, everyone. Like, if I don't see some of you on Thursday, again, thanks for coming. Like, you know, it was a good year. And say hi to me if you see me on campus. Brandon, what's up?
Yeah, I'm not going to the next lecture because I have to study for a 102 quiz, but I just want to say, like, thanks so much for being the prof. You're like my favorite prof on campus this year. And you've made like a genuinely positive impact on what I want to do for my future, which is really cool. I didn't expect that at all from my math prof. So yeah. Thanks. I really appreciate it.
Yeah, no, and I love hearing that too, because that's what you want to do as a teacher, right? Is you want to have that sort of impact. So that's awesome. Like, I love hearing that.
Yeah.
Okay. Yeah, no, awesome, everyone. Thanks so much, you guys. And like, seriously, you guys have been a great class. Like, I've had a lot of fun doing this. So, you know, if I don't see you, I don't see you. But like I said, you'll see me around campus next year, right? Make sure you come and you say hi. And again, I don't know what any of you look like because nobody turned on your cameras, but so just remind me who you are, okay? But yeah, everyone, okay, I'm going to take off here. Good luck with your exams if I don't see you. Okay, and for those of you who I do see, I'll be around on Thursday and come say hi to me. Okay, bye everyone.